Historically, everybody thinks about wildfire season as a specific time of year, right? It's the fall time frame. It's when the county is very dry, when we get our Santa Ana winds. But we now see that wildfires can occur at any point in time of year. Catastrophic wildfires can start any time of year. We've been working on wildfire mitigation for quite some time. A lot of our programs are very mature, but we constantly look at newer technologies to address wildfire risk across the board. We're constantly striving to do better in that area, realizing we've had a lot of success, but we need to build on that success and not be complacent. We serve all of San Diego County, about 4,100 square miles, including portions of South Orange County. A significant portion of our overhead system is running through our high fire threat district. These are areas where if you start a fire, it could become catastrophic, it could spread, it could be very destructive. If we talk about the overhead system, wires running overhead, a broken conductor that then falls to the ground causes an electrical fault, and that significant energy starts a fire. It's like a match in a dry brush, right? But that's essentially what falling conductors can do in an overhead system if no mitigations are applied. This is obviously something that electric utilities have had issues with since electricity was invented. This is a problem that needs to be addressed by the electric utilities. That's what brought about the development of the falling conductor patent here at SDG&E. Falling conductor protection is essentially utilizing algorithms through electric system measurements, current and voltage on the system, that aims to detect a broken wire, broken conductor, find out where it's located, and de-energize it before it can reach the ground. That's where SEL came in, has obviously been a trusted partner for a very long time. We've had great successes alongside SEL with a lot of other previous technologies that they've deployed.
At the heart of the falling conductor protection system is the RTAC, that's the real-time automation controller, which is the brain behind the algorithm. And the RTAC's located at the substation's central level.
I think the collaboration between both companies is great. There's nothing greater than working with a company that also manufactures the devices that we use in the system.
What really helped a lot, I think, where this project really took off was when SEL Engineering Services and SEL R&D developed this library that would make programming the falling conductor protection logic a lot easier and a lot easier to develop versus typing almost everything by hand.
We have synchrophaser technology out there in the field. 30 to 60 samples every second are taken at each measurement node, and that is time aligned via GPS clocks and all sent back to a data concentrator in the substation, which time aligns all of these different sensors. But being able to stream it also requires a pretty hefty IT network. So when we started falling conductor, we built up a radio network for a lot of these circuits, an FBDC network, and we've since evolved to deploying private LTE. All of the field testing has been very successful for each circuit. We've seen that everything that's been proven in the lab works in the real world.
To illustrate how the system works, let us consider an example. For a typical distribution pole that is 30 feet tall, we estimate about 1.37 seconds for the conductor to touch the ground. The instant the conductor breaks, the clock starts ticking. The phasor measurement units located throughout the distribution circuit are continuously transmitting synchrophasor data to the substation. We can consider about 50 milliseconds of radio latency one way. The synchrophasor data is concentrated in the SEL 3555 RTAC. The 5 voltage-based FCP algorithms continuously evaluate the incoming synchrophasor data for any abnormal voltage signatures. It takes the RTAC about 100 to 200 milliseconds to process a falling conductor event and make a decision. The RTAC then publishes an IEC 61850 goose trip command, which is transmitted to the PMUs in the field, and we can consider another 50 milliseconds of latency here. The PMUs take around 4 to 12 milliseconds to process the message and trigger the trip output contact, The breaker opening time may be anywhere in the ballpark of 80 milliseconds. The affected zone is successfully isolated, and the conductor is de-energized before the time it touches the ground. With a total round-trip time under 500 milliseconds, less than 50% of the 1.37 seconds that we started with.
This year we'll be at 10 circuits deployed in a test mode, but the goal is that by 2026 we're going to have all of our high fire threat district secure with falling conductor.
I feel like we've had a great relationship with SEL and being able to work in this project. We meet with them weekly at least, and every time whenever we have commissioning efforts, we're always in collaboration with them. I think falling conductor is a great technology that is can have a lot of great impact in the community.
This falling conductor protection system, along with a lot of other technology initiatives that our utility is striving for with companies like SEL, would mean safer power delivered to our customers and more reliable power to our customers as well.